In this lesson, we're going to look at one variable linear regression. Here we have the local ice cream shop that's keeping track of how much ice cream they sell versus the noon temperature on that day. In our figure of data, we have a left-hand column which contains the noontime temperature for each day that this was collected, and the right-hand column is the corresponding ice cream sales for each day the data was collected. On the first day, you can see that the noontime temperature was 14.2 degrees Celsius, and the sales for that same day was $215. Each one of these sets of values represents a point on our scatter plot. Let's take a look at the scatter plot. Here's our scatter plot. Our x-axis represents the temperature in Celsius, and our y-axis represents the dollar amount of ice cream sales for the day. So each one of these points represents a day in which the temperature was recorded and the corresponding ice cream sales were recorded. In this graph, a best fit line is drawn in blue. This best fit line is also called our trend line on our scatter plot. This is the line that we use to determine our linear regression equation. We model our line of best fit with our one variable regression model. Here's an example of the one variable regression model. yi is our dependent variable. Our dependent variable represents the sales in dollars for ice cream for the day. Let's move that up. Our independent variable is the noontime temperature in degrees Celsius. EI, or epsilon I, is our error term. B naught is our intercept coefficient, otherwise known as our y-intercept. And B sub 1 is our regression coefficient for the independent variable. This is known as our slope. Since our best line of fit is a straight line, we can think of it as the equation for a line. Y is equal to mx plus b, where m is our slope and b is our y-intercept. In this case, when we say y sub I, we are referring to the ith observation or data point. So this superscript I tells us which data point we're referring to. So yi is equal to beta with a subscript 0, that's beta naught, and that beta naught refers to our y-intercept or intercept coefficient, plus beta 1 or beta sub 1 times x superscript I, so this is the ith observation, the x value from the point I, the ith point, and our beta sub 1 refers to the slope of our line, plus epsilon I. And what this refers to is for any given data point, we have multiple data points, and they are xi and yi, and that represents the ith observation, which each observation yields a point in our scatter plot. So what happens is, since b naught and b sub 1 are fixed values, these are constants, and when we input our x value for any ith observation, we're going to get an approximation of what the corresponding y value is for that ith observation. This value here, e superscript I, that is our error term, otherwise known as our residual. And this is because this b naught plus b sub 1 times x, our x value, will only be an approximation for any corresponding y value. This is not a perfect fit until we add in our error. Our errors will only all be 0 for all observations if all of our points lie perfectly on our best fit line, on the line produced by our regression model. The best model, or best choice of coefficients for beta naught and beta 1, has the smallest error terms, or smallest residuals. Let's take another look at our best fit line and our corresponding scatter points. The residual for this point here, in order to calculate it, we draw a line from the point vertically up to our line of best fit. So the length of this segment is our error term. So that's epsilon for that point. And that's approximately equal to $100. This error is our actual value minus our prediction value. That makes this a negative 100 because our actual value for the point is approximately 440 minus the height of the line, which is approximately 540, and so the difference is a negative 100. Here we have another point that's above our prediction line. To get the error for this line, we draw a vertical line from our point down to our best fit line. There's our vertical line and the line segment. That segment is our error. So the height of our actual point, our actual value, is about 340, and we subtract the height of our best fit line or prediction line, and we'll call that 280, and the difference is 60. So here we have a positive error, and our positive error is 60. So we have, for our first point that we looked at, a residual or error of negative 100, and our second point we looked at, we have a residual or error of 60. We use our errors or residuals to help us determine the quality of our regression line, otherwise known as our prediction line. And we start by determining the sum of the square of our errors, otherwise known as the sum of the square of our residuals. If the number of points we have is n is the number of points or the number of observations, then so what we do here is we want the sum of the square of the errors. So we're summing up the square of each error. So for each ith observation, we will find the error and square it, and we will add this up from observation 1 to observation n. So the sum of the square of our errors is the square of the error from our point number 1, our first observation, plus the square of the area from our second point or second observation, plus the square of the error from our third point or third observation, plus, and we continue to add the square of each observation's error until we get to our last point, our nth point here, and we add the square of the error from our nth observation, and this gives us the sum of the square of the errors, or sum of the square of the residuals. We can also draw a horizontal line called the baseline model. In the baseline model, y is equal to a constant, and that constant is equal to the average height for each point. So if we sum up each one of our heights, y, for each observation, and that is from I equals 1 to n, the number of values, and we divide that by the number of values, we're going to get the average y value. Here I've drawn the baseline model. The baseline model predicts the average value of the dependent variable regardless of the values of the independent variable. The baseline model is a constant function, a horizontal line. The sum of squared errors for the baseline model is also known as the total sum of squares, commonly referred to as SST. SST is equal to the sum of the errors for each observation squared from ith observation 1 to the nth observation, in which we are adding up the distance this time between our data value and the baseline. So all values above the baseline will yield a positive error, and all values below the baseline will yield a negative error. When we square them, the square will actually be positive. And here we should have an I, indicating it's the error for the ith observation that is being squared. We use R squared to evaluate the fit of our prediction line. R squared is equal to 1 minus the ratio of the sum of the square of the errors divided by the total sum of squares. If r squared is equal to 0, then we say that there's no improvement over our baseline model. If r squared is equal to 1, then our prediction line is a perfect fit. As r squared gets closer to equaling 1, our prediction model becomes a better fit. R squared is nice because it's unitless and therefore universally interpretable between problems. When creating best fit lines through linear regression, we want to create lines that have R squares that are as close to 1 as possible.